It is simply impossible. But then, of course, the question that arises is there any way to make the equivalence class smaller? Is there any way for us to determine that maybe one model is preferable than the other? And the answer is yes. The way that we do this is by imposing structural knowledge that is based on either theory or research design. And when I use this term structural knowledge, what I mean is that we have some knowledge about the presence, absence, and direction of different arrows in these models. For example, you can ask yourself the question, was X randomized? And if it was, then you know that you can eliminate every single model that has an arrow going into X. Why? Because, well, if you randomize X, you basically force it to take on certain values, 0 or 1, or whatever you randomize over. It means that there is no other causal force other than you going into the system and twisting it that impacts X. That's why we all intuitively know why randomization is so powerful. As soon as you randomize, you can get rid of all of these models that have arrows going into X, which is a lot. It's a lot of models. You can try to make a case that X might be temporally and causally before M, or X before Y, or M before Y. You don't have a tool like randomization to do this, but you can make a theoretical argument. And as soon as you do this, you are allowed to eliminate all models that have directed arrows in the opposite direction. And lastly, can you assume that any pair of variables is unconfounded? And that is often a heroic assumption. But if you can make a case, if you can make a convincing case why you believe that to be true, you can eliminate all the bidirected arrows between the pair of variables that you assume to be unconfounded.